All right, think about standard binary for a second. We all know how to count up, right? Just adding columns of ones and zeros. But what happens when we need to go below zero? I mean, how on earth do we represent negative numbers inside a computer system using absolutely nothing but ones and zeros? It's kind of a giant puzzle. And today, we're going to solve it together using some incredibly clever logic.
Here's our roadmap for this explainer. 1. The negative problem. 2. Fixing the negative zero. 3. Understanding 2's complement. 4. The two-step inversion method. 5. Interactive binary quiz time. And 6. Common signed integer pitfalls. Let's jump right in.
Section 1. The negative problem. Going below zero.
So we know that in basic binary, adding a 1 to any column increases the total value. So, if adding 1s always makes a number bigger, how can we possibly flip the script to represent a negative? Well, think of a car's molometer. Picture a brand new car where the dial reads all zeros. If you drive forward 1 mile, it rolls to 0000001. But imagine you could force that meter backward 1 mile from 0. The digits would click backward and read 999999. We can basically interpret this massive string of nines as -1. And you know what? Computers use a really similar concept to wrap around zero.
Let's see how this actually builds into binary. Can you spot the pattern in these two lists of 8-bit numbers? Like, which bit tells us if we're looking at a positive or a negative number? Take a really close look at that leftmost column.
Did you catch it? In a signed binary system, that leftmost bit acts as our sign indicator. Notice how the positive numbers on the left always start with a 0, while the negative numbers on the right always start with a 1. And actually, since in mathematics 0 is considered a positive number, starting with a 0 aligns perfectly.
Section 2. Fixing the negative zero. Math anomalies.
Now, early engineers ran into some massive headaches when they first tried to build arithmetic systems using just a basic sign bit. When comparing the early methods, you'll see they tried simply flipping all the positive bits to make a negative. This was called 1's complement. But if you try to add 5 and -5 in 1's complement, instead of getting a clean mathematical 0, you get this really annoying off by 1 error. Check out the 2's complement results, though. When you add 5 and -5 using the 2's complement system, you carry the 1's perfectly across the board and get a pristine, beautiful row of zeros. The whole reason 1's complement failed in those early editions was due to a bizarre mathematical anomaly known as -0. You see, early systems actually had two different ways to write 0. You had a positive 0, which was 00000, and a negative 0, which was 1111. This bug was literally a nightmare for arithmetic. It essentially forced hardware engineers to invent a much better system that completely eliminated that -0.
Which brings us to Section 3. Understanding 2's complement, the ultimate solution.
Here is where it gets genius. In 2's complement, the leftmost bit, the most significant bit, or MSB, is no longer just a dumb sign label. It actually holds a true mathematical negative value. So if you have an 8-bit number, the standard column weights from right to left are 1, 2, 4, 8, 16, 32, and 64. But that final left column, it doesn't represent positive 128 anymore. It actually represents -128. This mathematically grounds the entire system.
Let's break down why that works so beautifully. When comparing these 4-bit numbers, our leftmost bit is now the -8 column. So to get -4, we place a 1 in the -8 column and a 1 in the positive 4 column, because -8 plus 4 equals -4. Look at how seamlessly the binary patterns just count up from -4, right through a single clean 0, and straight up into the positive numbers without any glitches or duplicate zeros.
Section 4. The two-step inversion method. Finding the negative. Okay, I'm going to give you a foolproof way to manually convert any positive binary number into its negative equivalent. Here's the standard two-step process. Step 1, you invert all the bits. Literally just swap them. Every 1 becomes a 0, and every 0 becomes a 1. Then, step 2, you simply add 1 to that inverted result. Now, while it takes a little bit of manual work for us humans on paper, doing this inverting and adding is something that computer hardware does absolutely effortlessly.
But I do want to share a surprisingly brilliant shortcut trick from our sources. This is a real game changer for your toolkit. Starting from the right-hand side, the least significant bit, you just copy each digit exactly as it appears, up to and including the first one you come across. After you've written down that first one, you just flip every remaining bit as you move to the left. 1s to 0s, 0s to 1s. It works perfectly every single time.
Section 5. Interactive binary quiz time. Test your skills.
I absolutely love this stuff.
I want you to actively test your new skills right now. Go ahead and pause this explainer, grab some paper, and let's do some math together. Here's your first practice challenge. I want you to convert positive 12, which in 8-bit binary is 00001100, into negative 12. Try applying either that standard two-step inversion method or the neat shortcut trick we just learned. Take your time.
All right, let's see how you did. Negative 12 is 1110100. If you use the shortcut trick, you'd copy the 0, and the first one starting from the right, and then you just flip everything else to the left. Oh, and always do a quick sanity check. Did your leftmost sign bit appropriately end up as a 1? Yes, it did. Okay, let's hit a snappy second challenge. Let's convert positive 5, which is 0101, into negative 5. But this time, we are strictly using 4 bits. This is going to ensure we really grasp the scaling context of binary lengths. Give it a shot. Let's review the answer. Negative 5 in 4-bit binary is 1011. If we follow the standard step-by-step method, we start with 0101. First, we invert everything to get 1010, then we just add 1 to that final bit, bringing us perfectly to our final state of 1011. Fantastic work if you nailed that.
Section 6. Common signed integer pitfalls. Avoid these traps.
I want this to act as your personal study guide, so you can successfully navigate those tricky exam questions without dropping easy points. The absolutely crucial thing is to avoid these 4 common traps. Pitfall 1, forgetting that the most significant bit actually has a massive negative value, like -128. Pitfall 2, doing the inversion but forgetting to add that final +1. Actually, scratch that, it's super common to forget that part. Pitfall 3, panicking about the final carry bit that overflows when you add a positive and negative number together. Just ignore that overflow bit entirely. And pitfall 4, not checking how many total bits you're actually supposed to be working with. And that last point is exactly why this quote is so critical. As our sources emphasize, it's important to know how many bits you're working with so you know which bit indicates the sign. Context literally dictates everything here. If you don't know the exact length of your binary string, like whether it's 4-bit or 8-bit, you cannot know which column holds that heavy negative weight.
You have accomplished so much today, grasping the truly elegant logic of 2's complement, but I want to leave you with this final provocative thought. If 2's complement completely perfected integer math, meaning whole numbers, how on earth do computers represent negative decimal numbers, like -3.14? It's a whole new puzzle, and I know you'll be eager to decode floating point numbers next time.